Cheap, fast computers have brought down the cost of everything from prototyping to tech support. But some challenges can't be solved with computation alone. Take nuclear energy, for instance. It isn't as cheap as it could be. If engineers can design pressure vessels that can last longer, the high costs of building a power plant could be spread out over a longer time. The pressure vessel is the steel tank that contains the reaction that drives the whole plant. It holds the core. The steel of the pressure vessel holds in high pressures of hot water and steam, all while being hit by radiation. If we want to build a better pressure vessel, we'll need to take a closer look at how they fail, and what changes about the crystalline structure of the metal. Normally, each metal tends to organize atoms in a specific way. For the most part, this leads metals to repeat one pattern over and over. But every now and then, an atom gets out of place, and sometimes whole groups of atoms get out of place, and patterns that start in different places don't often match up. When any of these things happen, we call it a defect. A single atom out of place is called an interstitial because it squeezes itself between other atoms in the pattern. Interstitials happen all the time in metals. Because of another defect, called a dislocation, metals can bend before they break. Whenever dislocations move through the structure, they can change the pattern to allow the whole piece of metal to change shape. It can be hard to visualize these defects if you're just looking at your spoon, so let's look at Manhattan. City blocks have a pattern, like the atoms in a metal, and if you zoom in, we can take people to be interstitials, and cars to be dislocations. The nuclear core of our power plant radiates a flow of neutrons into the walls of our pressure vessel. Sometimes these neutrons knock into an atom, sending it out of its pattern and turning it into an interstitial. As the metal gets irradiated, more and more interstitials are created, until they become as crowded as people in Times Square. Interstitials can make it harder for dislocations to move. They can get in the way. Since our metal can only bend if dislocations can move, the buildup of interstitials can make our metal brittle, like glass. This is bad news for pressure vessels. If dislocations get enough energy behind them, they can move interstitials out of their way. Watch this car. See how it takes a while to get the interstitials out of its path, but once it does, it can move, and so can all of the other cars behind it. When it happens in a metal, we call it strain localization. Now, what you won't see here is what happens after this. As the dislocations move, defects accumulate on the edges of the clear path. Eventually, this forms cracks, which can then grow quickly through the brittle metal. This means failure for our pressure vessel. Overcoming challenges like strain localization will require the work of material scientists and others. New, highly designed materials will be required to meet the demands of the inventions of the future, and to give form to what might be.